All right, so we're in section 2.6 now, and we are looking at limits at infinity and horizontal asymptotes. We've dealt with limits that have involved the idea of infinity already, and they showed up in the topic of vertical asymptotes. We showed that if you have a limit of some function as x approaches some real number, and that limit comes out equal to what we're calling infinity, what that means is that the function is growing arbitrarily large as x gets close to that value. This is a different way of using infinity. In this case, we're going to be talking about the limit as x itself approaches positive or negative infinity. And we'll get into more detail on that in a minute, but let's start with an example to sort of illustrate this. These limits at infinity that we're talking about in this section concern an aspect of functions that we call end behavior. So end behavior is what happens to a function f, as we're typically going to call it, as x becomes arbitrarily large, which we think of as approaching infinity, or arbitrarily small. And by small, we don't mean close to zero. By small, we mean approaching negative infinity. So numbers that are very far in the negative direction is what we mean by small. I want to point this out. I think I mentioned this in a previous video, but I'm just going to reiterate it here. This is just terminology and a symbol. So when we use the symbol infinity, it's really important to keep in the back of your mind that infinity is not actually a number, and you can't approach infinity. You can't literally do that. It's tempting to think that, as numbers get larger and larger, we're getting closer and closer to infinity. But by its very nature, the number 2 is no closer to infinity than the number 1 trillion. Neither of those are any closer to infinity than the other because you cannot approach infinity in a literal sense. So when we say approaches infinity or approaches negative infinity, we're sort of running with an intuitive idea of what that means, even though it's technically not something that you can do. So by approach infinity, we mean x is getting arbitrarily large, and similar for negative infinity. Let's start by looking at a rational function to sort of get into the main idea behind this section. F of x equals x squared minus 1 over x squared plus 1. If you were to graph this in a graphing calculator or Desmos or something like that, you would get this curve. You wouldn't get the red line. I put the red line in there myself, but the purpose of that red line is to show that this graph has what's called a horizontal asymptote. Our curve, as you can kind of see, going either direction, towards the left or towards the right, appears to be approaching that red line. And as you know from algebra and pre-calculus, if you took that, the purpose of an asymptote is to tell us in the long term what a curve is approaching. So our blue curve is approaching y equals 1, that horizontal line. And in this case, on either side, it's going to remain below that line at all times, but becoming arbitrarily close to it. And again, by arbitrarily close, we mean as close as you want to make it. You can make the blue curve as close to the red line as you want to, as long as you go out far enough. Now, other cases of graphs with asymptotes, horizontal asymptotes in particular, it may actually happen that the curve crosses that asymptote. It may do it multiple times. The purpose of a horizontal asymptote is not to tell us what's happening with a function locally, which means at any specific little interval that we want to look at. It's telling us what's happening long term. A lot of times people fall into the misconception that a curve cannot cross a horizontal asymptote. It absolutely can, but in the long term, it'll eventually have behavior that looks like this, where it just approaches that horizontal asymptote. Okay? Now, we are going to frame horizontal asymptotes in the language of limits. So what we're seeing in this graph here is that as x gets arbitrarily large, which we're going to think of as approaching infinity, and again, technically that's not what's happening, but we're just going to call it that, or as x approaches negative infinity, as x becomes arbitrarily small, in either case, our function f of x is approaching 1. So we use this notation to illustrate either of those. The limit as x approaches infinity of our function equals 1. That means as I go arbitrarily far to the right, my function is becoming arbitrarily close to the number 1. The limit as x approaches negative infinity of our function is also equal to 1 because the same thing is happening as we go to the left. Now I should mention, you're going to see an example of this in a little bit, even though in this case the horizontal asymptote applies to the end behavior of our function as we go towards infinity or negative infinity, that is not necessarily the case with all functions. Some functions will have a horizontal asymptote that only applies to what's happening as x approaches infinity, but maybe as x approaches negative infinity, the function doesn't have a horizontal asymptote. In other cases, a function might have two horizontal asymptotes. As we approach infinity, the function goes one direction, and as we approach negative infinity, the function might go a different direction. But in this case, the same horizontal asymptote happens to work for both directions. Okay, so here we give our intuitive definition for a limit at infinity, which is kind of what we just talked about. Let f be a function that's defined on some interval a to infinity. So some interval that contains real numbers extending all the way to the right. Then the limit as x approaches infinity of f of x is equal to L means that the values that we get from f of x can be made arbitrarily close to L, that's the term I keep using, arbitrarily close to L, by requiring x to be sufficiently large, meaning sufficiently far in the positive direction. Okay? We have a similar definition down here for x approaching negative infinity. If the limit of that of f of x as x approaches negative infinity equals some finite number L, it's telling us what our function is doing as we move arbitrarily to the left. Okay? And then I've already used this terminology, but the line y equals L is called a horizontal asymptote of this curve if either the limit as x approaches infinity or the limit as x approaches negative infinity equals L. And remember, sometimes, as in the case we just looked at, both of these limits will equal L, but this definition doesn't require them both to equal L, just one or the other at the very least. Okay? So here's an example. In this example, we want to look at the horizontal asymptotes of the function y equals inverse tangent of x. Now, the inverse tangent function is defined on all real numbers, but its range is the open interval from negative pi over 2 to pi over 2. This is something you learn in trigonometry. Hopefully you've also seen what the graph of the inverse tangent function looks like. This is it, if you haven't seen it. So just looking at the graph, what is the end behavior of this function? What's happening as we approach arbitrarily far from the right, or arbitrarily far in the positive direction, or arbitrarily far in the negative direction? Well, I've highlighted the horizontal asymptotes in this case. As we approach infinity, as x approaches infinity, y is approaching pi over 2. As x approaches negative infinity, y is approaching negative pi over 2. So those would be the horizontal asymptotes. Y is equal to pi over 2, and y equals negative pi over 2. Okay? So this is an example of a function that has two different horizontal asymptotes because we're approaching something different as we go to the right compared to what we're approaching when we move to the left. Okay, here's another example, and again, we're going to look at this one graphically. Identify all asymptotes of y equals 1 over x cubed. Notice it doesn't just say horizontal asymptotes this time, it says all asymptotes. Okay, so in this case, I could frame things in terms of limits here, but since we have a graph to look at, I'm just going to use what I can see graphically. I can see that we appear to have a vertical asymptote at x equals 0, so at my y-axis. I'm going to say vertical asymptote at x equals 0. Now, a vertical asymptote is a description of local behavior. I don't need to go infinitely far to the right or to the left to see what's happening in this little region right here. I can see that my function is blowing up in either direction as we approach 0. Now, horizontal asymptote. I'll do that for asymptote. As we move either to the left or to the right, we see that the end behavior of this function is that our graph appears to be approaching the x-axis. here, and here. So that's the line y equals 0. Only one horizontal asymptote in this case, but it applies to either direction, okay? And again, I could have framed this in terms of limits and stuff, but because we have graphs to look at, I can just use the visual and identify those asymptotes pretty easily. Okay. Sometimes we're not going to be looking at a graph, and so we need to be working with a function algebraically, and this theorem is going to help us with that. If r is greater than 0, and if it's also a rational number, then the limit as x approaches infinity of 1 over x to the r is equal to 0. And then similarly, if r greater than 0 is a rational number such that x to the r is defined for all x, then the limit as x goes to negative infinity of 1 over x to the r is equal to 0. So this is dealing with x approaching negative infinity as opposed to positive infinity. The reason there seems to be more wordiness in this second half of the theorem is because if x is approaching negative infinity, then we are plugging negative numbers. If we were doing this numerically, we're plugging negative numbers in for x as opposed to positive numbers here. If r is a rational number and x is any positive number, you can always raise x to the power of r. There's never a problem with that. But when x is negative, depending on what that rational number that we're using in our exponent here happens to be, this may not be defined. For example, if r is equal to 1/2, that's a positive rational number. If I plug negative 1 in for x, that's negative 1 to the 1/2 power, or the square root of negative 1. That's not defined in the real numbers anyways. You know that it's equal to the complex number I, but we don't deal with complex numbers in calculus, at least not at this level. That's handled in a very different way. So we would simply say that it's not defined in this class. So let's keep this in mind, and let's think about why this is the case also. So what happens to an expression like this as x approaches infinity? Well, as x approaches infinity, that means we're plugging in larger and larger positive numbers for x. Raising that to r, regardless of what that rational number in the exponent happens to be, this fraction will become smaller and smaller as x becomes larger and larger. Smaller in the sense that it's approaching 0. So that intuitively is why we would expect this limit to come out to 0, and the same reasoning works here as well. We saw this up here. Notice that this is an example of that type of function that we're talking about in that theorem, 1 over x raised to some rational number power. In this case, that rational number is the number 3. And we see that both in the graph and intuitively. If I plug in, for example, 1 into this function, I get 1 over 1, which is 1. Okay, but then if I plug in a larger number, say 10, now that's 1 over 10 cubed, or 1 over 1,000. 1/1000th is much, much smaller than 1. Then if I plug in larger and larger numbers, 100, 1,000, 1,000,000, whatever, this denominator is going to be getting very, very large as x gets large, creating an overall very small positive fraction. So that's why we see this function approaching 0. And similar reasoning shows why it's approaching 0 from this side. So intuitively, it makes a lot of sense why this is true. And we can use this to evaluate a lot of limits without needing a graph. So here's an example. I like to evaluate this limit. The limit as x approaches infinity of this cubic function, 4x cubed minus x plus 5, over another cubic function, 3x cubed plus 7x squared minus 1. Okay. Notice I don't have a graph to look at. So this is the first limit as x approaches infinity that we've looked at so far, where we can't come up with an answer from the graph. What I'm going to do here is modify this function. So the limit as x approaches infinity, and I shouldn't say modify, but I'm going to simplify it in a specific way. 4x cubed minus x plus 5 over 3x cubed plus 7x squared minus 1. What I'm going to do is a common trick we've already used multiple times, and you would have used this in several other classes prior to this one. I'm going to multiply this by an expression that's equal to 1, because we already know that wouldn't change the value of anything here. Specifically, I'm multiplying by 1 over x cubed over 1 over x cubed. Okay? Now notice what this does. the limit as x approaches infinity, of, when I do that, 1 over x cubed times 4x cubed is simply 4. Multiplying it to this negative x here gives me 1 over x squared plus 5 over x cubed. Okay? Down here, when I multiply 1 over x cubed to my 3x cubed, I'm just going to be left with 3 plus 7x squared times 1 over x cubed would be 7 over x, and then finally minus 1 over x cubed. That's what I would get. Okay, at this point I want to use my limit laws, and those limit laws, even though I haven't stated that here, those limit laws that we talked about back in section 2.3, even though none of them were stated using a limit at infinity, they all apply to limits of this type as well. So what that means is that I can bring this limit into my numerator and my denominator and use it to evaluate the limit as x approaches infinity of each one of these terms individually. Now, I already know that the limit of a constant, regardless of what x is approaching, is always equal to that constant. So the limit as x approaches infinity of 4 is simply 4. Same thing with this 3 down here. But what about these other terms? Well, all of these terms, if I factor out the numerator at least, is a function of the form 1 over x to the r, right? So each one of those, according to this theorem, is going to go to 0 as soon as I apply that limit. That goes to 0, that goes to 0, that goes to 0, and that goes to 0, leaving me with the limit as x approaches infinity of 4/3 being constant. That's simply 4/3. Okay? So backtracking a little bit, how did I know to multiply by 1 over x cubed over 1 over x cubed? Well, all I did is I found between my numerator and my denominator what my highest degree term was. And I multiplied by 1 over that power function, 1 over x cubed. If I had an x to the 5th showing up somewhere in here and all of the other x's had a smaller power on them, then I would have used 1 over x to the 5th. But it's whichever term has the highest degree, I multiply by the reciprocal of that. Okay? Here's another example. I want to find the horizontal asymptotes of y equals the square root of x squared plus 3 over 5x minus 2. So this one looks kind of similar to the previous example, but I'm noticing that I have this radical here, which is not, it's a little different than what we saw up here, okay? So what I'm going to do is something similar. First of all, we're looking for the horizontal asymptotes of this, which means I'm looking for the limit as x approaches infinity from either direction. The limit as x approaches infinity, excuse me, of this function is going to be equal to, let's just rewrite it first, square root of x squared plus 3 over 5x minus 2. Okay. Now, there's one thing that, well, actually, let me wait until I get to the negative infinity to talk about that. Sometimes when we do this simplification, you do need to be careful about whether we're approaching a positive infinity or a negative infinity, because you want to think of those numbers that are being plugged in for x as either very large positive numbers or very small negative numbers. Okay, so what I'm going to do here is think that I'm plugging in very large positive numbers for x. Now, if I did that, regardless of what I plug into my numerator, unless it's equal to 0, which it won't ever equal 0, the square root of something always comes out positive. My denominator can be positive or negative depending on what I plug in for x. But if x is a very, very large positive number, which is what we're looking at here, then 5 times that minus a small number like 2 is still going to be positive. So I'm expecting my limit to come out positive because I have positive over positive. Having thought that through, I'm going to do something similar to what I did up here, But this time I'm going to multiply by 1 over x times over 1 over x. Now you might be looking at that and think, why didn't I multiply by 1 over x squared? After all, the highest power that I'm seeing is an x squared. And the reason for that is because this numerator is not just a polynomial. In my previous example, I had polynomials. In this case, I have a polynomial under a radical. And so what I'm doing is I'm thinking down here, the highest power on my x is a 1. Up here, that x squared, I don't want to just think of it as an x squared. Think of it as the square root of x squared, which simplifies to the absolute value of x. Although since x is positive, that would just be x. So x up here, that's why I'm multiplying by 1 over x over 1 over x. What happens when I do that? The limit as x approaches infinity. How do you bring a 1 over x into a radical? Well, once you bring it into that radical, it becomes 1 over x squared. So what is that equal to? That's equal to 1 over x squared times x squared plus 3. That's what's going to be on the inside there. Down here, 5x times 1 over x is 5, and then I have minus 2 over x here. Let's distribute this 1 over x squared in. So I'm going to get the limit as x approaches infinity of the square root of 1 plus 3 over x squared. 5 minus 2 over x. Okay? Excuse me. So now, if I were to bring my limit into my numerator and denominator, from my limit laws, I know that I can also bring that limit into this radical and then individually to each of these terms. These two terms are going to go to 0. And what I'm left with is the square root of 1 over 5. Remember, the limits of those constants are just equal to those constants. Of course, this is the same thing as 1/5. Okay? Now, one thing you can do if you're unsure about the limits that you're doing in this section is you can take out a graphing calculator or Desmos if you're online or something like that and graph the actual function itself. And then look at that function and see if you can visually see a horizontal asymptote that agrees with what you found here, okay? Now I circled this. I shouldn't have circled this now that I'm thinking about it because I want my asymptote to be written in the form of a line. So y equals 1/5 is the correct asymptote to use there. Now I don't know yet if I have a different asymptote as I approach from the left, right, as I approach negative infinity. So we have to investigate that also. What is my limit as x approaches negative infinity of this function? X squared plus 3 over 5x minus 2. What'll that come out to? Well, it's the same function, so I would simplify it in the same way. This is equal to the limit as x approaches negative infinity of this guy right here, 1 plus 3 over x squared over 5 minus 2 over x. Now the tricky thing here, because if I were to bring this limit up and into each one of these guys here, it would appear as though I'm simplifying to 1/5 again, because still both of these are going to go to 0. But going back to my original function, it really wouldn't make sense for this limit to come out to be a positive number. Because remember, what we're doing when we evaluate a limit as x goes to negative infinity is we're using very, very small negative numbers, numbers that are very, very far in the negative direction. And again, this square root up here can only come out positive. But if I plug in a very, very small negative number, negative 1 million, for example, then 5 times that would be negative 5 million minus 2, still a negative number. So very, very small negative numbers are guaranteed to put negative numbers in my denominator, and a positive over a negative is equal to a negative. I should be expecting a negative result. So instead of getting 1/5, I have to remember that my result should be coming out negative. I should get negative 1/5 as an answer. And that tells me that my other asymptote is y equals negative 1/5. And again, I would recommend graphing your function to see that we get both of these asymptotes in your answer. Okay, I'll move on to this next example in the next video.